Okay, so rotational motion.
High wire artist Carl Walenda, possibly the world's best-known circus performer, fell to his death today doing an outdoor stunt in Puerto Rico. For that, here's James Walker.
The only place I feel alive, said Carl Walenda, is on the wire. And there he was this morning, 73 years old, 120 feet in the air, 10 stories above San Juan, performing as he had for 58 years. The idea was to promote a circus act he was performing with his granddaughter. So, a high wire walk across the street from one beachfront hotel to another. But as he reached halfway, the ocean wind suddenly picked up, gusting to 30 knots. And Carl Walenda, the best man in the world on a high wire, fought for his balance. "200 people saw Walenda fall. Many rushed to help, but it was too late. Walenda's body had struck a parked taxi. He was dead on arrival at the hospital." Carl Walenda and his family came to the United States from Germany in 1936, brought here by John Ringling and the Ringling Brothers and Martiman Daly Circus, which was their home for the next 18 years. It was a family act, but Father Carl was a star. Frequently, he appeared alone, like in this stunt when he walked across an 1,100-foot cable, strung 700 feet above the Tallulah Gorge in Georgia. He was so supremely confident that he did it wearing a microphone to narrate his own crossing.
It's a little windy now. More wind than I expected. God is with me. I believe everything will be all right.
Carl Walenda is the fifth member of the family to die while walking the high wire, the latest in a series of tragedies that began in 1962 with a seven-man pyramid, developed and perfected by Father Carl. During a Detroit appearance, the pyramid collapsed. 2 family members fell 40 feet to their death. Carl's son Mario was permanently paralyzed. And Carl Walenda did not escape untouched. He suffered a broken pelvis and a double hernia, but he always returned to the ring and his high wire. This afternoon, Carl Walenda said that despite his uncle's death, the act will go on. James Walker, ABC News.
His final performance. At 73, a high wire walk 10 stories up to promote a circus appearance with his granddaughter. The patriarch of the great Walendas was best known for the creation of their 3-level human pyramid. It was also their most dangerous act. This happened in practice. In 1962, the pyramid collapsed for real. 2 were killed and an adopted son crippled for life. Despite it all, Walenda told interviewers he was not afraid.
Well, even in a big fall when I lost 2 people to get killed, and my son is paralyzed for life. And I never failed. And 24 hours later, I was up on the wire with a broken pelvis bone.
The Winnebago County Board.
All right, so here's a question for you.
High wire artist Carl
Across the street from 120 feet in the air. The idea was to promote a certain world on a high...
Okay, guys, what's the purpose of the poll? What does it do for you?
Give him balance.
Absolutely, give yourself 5 points. How? How does a poll like that give you balance? Where do you get the balance from?
Wire fought for his balance.
Oh, Walenda. All right, so obviously the high wire act requires a pole, and these poles are fairly lengthy and massive too. So the question is, how do they work? How do they give you balance? In a centrifuge is accelerating, right? Acceleration is 12 sheets. What kind of acceleration is this? Is this just centripetal acceleration, or is there also rotational acceleration that goes on? Because notice that he's actually accelerating rotationally as well. So there are 2 types of accelerations at play here. So one is the centripetal acceleration, the other one is the rotational acceleration. So what's a rotational acceleration? All right, so let's talk about angular displacement. Angular displacement just simply means angle in this case. Angular displacement. All right. So you got your angular displacement. That's the angle that you're looking at, just data. R is going to be the radius. You take look at you got the okay. So R is going to be the radius, and this point is going to sweep in this direction. It's just going to go up in this direction. It's known as the arc length that you're looking at. All right, so if you know the angle and multiply with the radius, it's going to give the arc length. All right, so R, this is going to be your arc length. R is going to be your radius. Theta is your angle. Instead of saying angle, we say angular displacement. Angle is going to be expressed in terms of radius. All right, so instead of degrees, we end up using radius. All right, so you got 2 pi radians, which is the same as 360 degrees. So 1 radian is going to be 360 degrees divided by 2 pi. That's what it means. All right, so 1 single revolution is going to be 2 pi radians, 360 degrees. All right, so a couple of things. Understand that 2 pi radians is 360 degrees. 1 revolution is going to be 2 pi radians. Okay, so physics-wise, this chapter is actually fairly easy. The terminology is something that you have to kind of get used to. All right. So that's your angular displacement. Now we got angular velocity. So angular displacement is going to be the angle expressed in terms of radians. Angular velocity is how, remember velocity is how fast the object moves from one point to the next point, how fast it's measured distance over measured time. All right. So angular velocity is how fast the angle changes, angular displacement changes. It goes from an initial value to your final value. So how fast the angle changes or angular displacement changes in time is going to be your average angular velocity. All right, so there's going to be an angular velocity. It's called this omega, obviously it looks like W. All right, so the omega in this case represents the angular velocity. We use, for angular terms, we use the Greek letters. How fast the angular displacement changes in time is known as angular velocity, the average velocity or the angular velocity. So it's your angular velocity. Theta is going to be your angular displacement. It's going to be time. So angular velocity is going to be, angular displacement is going to be radians. Angular velocity is going to be radians per second. Radians per second. So that's what we got. So how fast the angle changes in time, how fast the angular displacement changes in time. So the next topic is the angular acceleration. So angular acceleration is how fast the angular velocity changes in time. So here's your initial angular velocity, and then in this direction, it's just going to speed up. How fast the angular velocity changes in time. So within this time period, it's going to go from this angular velocity to the next angular velocity. So how fast the angular velocity changes in time. All right, so Greek letter alpha is what we use for that. So that's your angular acceleration. Omegas will be the angular speeds or the velocities. T represents time for you to go from an initial to a final angular velocity. All right, so angular velocity or speed is going to be in terms of radians per second. Angular acceleration is going to be radians per second squared. All right, let's take a look at problem number 1 from the handout. Okay, so we'll have to kind of get used to the conversions. The only trick or tricky thing in this chapter is the conversions, literally. So what we have, we got a blender. Okay, it's got blades, so the blades are rotating at a rate of 6,500 revolutions per minute. RPM is revolutions per minute. And then the motor is turned off, so which means that the blades will slow down to a stop within 3 seconds. So they will go from 6,500 revolutions per minute to 0. So what's the angular acceleration as the blades are slowing down? Okay, so initial angular velocity is going to be 6,500 revolutions per minute. Now obviously slowing down to a stop, so the final one is going to be 0. Proper unit is going to be radians per second. So this is going to happen in 3 seconds. So what's the angular acceleration? All right, compared to other problems that we've done so far, these problems are really, really easy. All right, so everything that we've done like 10 weeks ago or 12 weeks ago, okay, now those problems should be fairly easy. We were doing it using the rotational motion. All right, so one single revolution is going to be 2 pi radians. I have to express things in terms of radians per second. And what else? We got 1 minute per minute. 1 minute is going to be 60 seconds. All right, so radiances will cancel. No, the revolutions will cancel, and the minutes will cancel. So it's going to give you radians per second. Okay, so that's it. That's the only trick involved so far. All right, so angular acceleration is how fast angular velocity changes in time. So final angular velocity is going to be 0, like the numbers in. And we got the acceleration. So the first problem was easy. All right, for whatever reason, if you failed this chapter, and hopefully you won't, the math section of it. Okay, guys, upgrade test questions kind of look like this. They're not that complicated. All right, I'll give you some hints on that one. Okay, so let's build on. Build on. What do we have? Okay, so combination of angular and tangential variables, tangential angular variables, whatever that is, will be fairly obvious right now. So this point is moving in this direction, so there's going to be an angular displacement in that direction. Angular displacement is going to give you the arc length. How do you get the arc length? All right, so you get the arc length if you know the angular displacement. If you know this, multiply by r, it's going to give you the arc length. Okay, so you got an angular variable, which is theta. If you multiply by r, it's going to give you the tangential variable, which in this case is going to be the arc length we're looking at. Moving forward. This one is at angular velocity. Okay, if you want to know what the tangential velocity is right at this point, at that point, what you need to do is take the angular velocity and multiply it by r. It's going to give you the tangential velocity. Okay, so if you know the angular term, if you multiply it by r, it's going to give you the tangential. Okay, so tangential distance here, distance here, distance here is going to give you the arc length. And tangential speed. Tangential means that it's a vector, it just touches the curve at a single point. Okay, that's what it means. So how fast it's moving right at that point, how fast it's moving at that point. So these are like the linear speeds. So if you know the rotational speed, you can figure out the linear speed at any radial distance. In essence, so it's going to give you the tangential speed. Okay, so this thing is accelerating in this direction, so it's getting an angular acceleration. If you wanted to know what the acceleration is at any point along this radius or radial distance, the thing you have to do is just take this angular acceleration and multiply it by radial distance with respect to the point of rotation, it's going to give you the tangential acceleration at that point. All right, guys. So you got theta, you got omega, and you got alpha. Okay, so those are the angular variables. If you take an angular variable and you multiply by the radial distance, it's always going to give you the tangential variables. All right, so you can go from angular to the linear variables very easily. All right, so v sub t is going to give you the tangential velocity. V sub t is going to give you the tangential acceleration or the linear acceleration. All right, so that's how we do the transitions from angular to the tangential. Topic number 1. Okay, oh man, this is an exciting problem. So what do we have? We got a bicycle. All right, and it's going to be traveling 8 kilometers. It's about 5 miles, I think. Okay, so how many revolutions do the wheels make? We know something about the diameter, and we know the distance it's going to travel. So how many revolutions will the wheels make? So that's what we want to focus on. That's weird. Okay, moving forward. So diameter is going to be twice the radius. It's going to be twice the radius. Okay, this is weird. Okay, PowerPoint is doing this one thing. Hold on. Right, so we need to get the radius out of this. So divide the diameter by 2. So we got the radius. All right, so the total arc length of this S is going to represent the total distance traveled by the wheel, one single wheel that we're looking at. It's going to be 8 kilometers, expressed in terms of meters. So express the angle in terms of the number of revolutions that we will have. So find the angular displacement, total angular displacement in order to travel this distance, and express it in terms of number of revolutions. All right, so S is going to represent the total distance. R is going to be the radius, and then theta is going to be the angular displacement. All right, so find the angle and express it in terms of radians. And then take the radians and express it in terms of revolutions. One revolution is going to be 2 pi radians. And then it's going to give you about 4,000 revolutions. Okay, the thing that I'm just noticing that's one of the difficult things about doing these problems numerically. I think that's something that I need to emphasize. I think I'm going to be emphasizing it in the next problem. When you do a transition from radians to revolutions, notice that you're dividing everything by 2 pi radians. You have to write out pi as a number. So you have to make sure that every time you're using pi, you're using 3.14. All right, so that's what you need to do, or else you're not going to be able to get the numbers. All right, so rotational motion. Now there are 2 accelerations at play here. One of them is the centripetal acceleration. The other one is the rotational acceleration. So we will be dealing with 2 different values. And the number that you're looking at on the side, that's 12 G's. 12 G's is the total acceleration. So it's going to be a combination of the rotational acceleration as well as the centripetal acceleration. All right, so let's focus on those concepts. All right, so if this thing is moving at constant speed, it will have centripetal acceleration. So it's got a tangential speed. If that's the case, it's just going to give you centripetal acceleration. All right. If life is that easy, if this thing's not speeding up, slowing down, if it's just moving at a constant speed, if it's got a constant tangential speed, it's only going to give you a centripetal acceleration. So that's the only case that we dealt with before. All right, so we can express the tangential speed in terms of the angular speed. Remember, angular speed times the radial distance is going to give you the tangential speed. So let's just modify this formula a little bit and come up with an expression for the centripetal force in terms of the angular speed. So I'll do a back substitution. Let's do this entire expression is going to become squared. And you got r squared and r. All right, so square and r will cancel. Okay, so now we got a second expression for the centripetal acceleration. Okay, not only it's the square of the tangential speed divided by the radius, but also the radius times the square of the angular velocity, or speed in this case. All right, so we can have 2 expressions that we can use at our disposal at this point. So A sub c is our centripetal acceleration, r is our radius, omega is our angular velocity.